We are live on YouTube, guys, so be careful what you say. And recording is about to start. I believe the recording has started. All right, guys, are you? I hope you guys are all seeing my screen. I'll increase the font size. Is this font size okay, or should I increase it a bit more?
I think one more.
One more. All right. How about this, guys?
Yeah, it's
Good
good.
for me.
Okay.
I have a large screen.
So I'll just recap about the river data set. We went through all of it. What did we do? We did the standard imports, no changes. We loaded the data, and this by now, I'm just repeating so that it becomes second nature. We did some profiling of the data, and where's the profiling of that data? Okay, for some reason it's not visible here. So then we built a naive logistic model, which failed. Then we did polynomial and logistic, which led to some degree of success. And finally, we did a more careful analysis. In a more careful analysis, we went to, and that more careful journey was through regression. And it just illustrates that quite often when you solve a problem, you can take all sorts of indirect routes to finding the solution, building a good model to it. So when we did that, I remember that we had some confusion matrix and values classification. We got close to 90% accuracy, which is impressive. Right? So that kind of accuracy. Now, what is ROC curve? It just gives you an idea of how good your model is. You want the line to have the top left corner. It seems to be doing that. This is the number of mistakes you are making. Once again, the number of mistakes we are making is small. So feature engineering worked. Then we tried decision trees. Decision tree to do it again is just a couple of lines of code. Now there are a lot of things you can tune. Like for example, here I wanted to make a relatively simple decision tree. I said max depth is equal to 5. If you don't set that depth is equal to 5, it will make a very, very complicated decision tree. Depth 3, 4 even, maybe. So when you do that, you realize that this is actually visibly worse than feature engineering. And there are quite a few mistakes. When you do model diagnostics, you realize that you get uh, uh, the accuracy. Actually, yeah, you'll get some accuracy and some. This is for, I think we moved now to random forest. I already moved beyond decision tree. This is random forest, and then, oh no, it's decision tree. I think I have run this class in a different order. So something is off. Anyway, I'll post the rerun everything and post the latest version. Today, what I wanted to show you is how would you apply a support vector machine classifier to this data. I've applied the SVM classifier to the river data, and I have applied the SVM classifier to the California housing data. Remember, river is a classifier problem. California housing is a regression problem. We're trying to predict the median house value. So with that in mind, you realize that from a code perspective, it's very straightforward. You go and build a model. Once you build a model, you use it to predict. Once you predict, you go and get the confusion matrix. Once you get the confusion matrix, once again, you create a classification report and you get about 80% uh, SVM model that is 80% accurate. Now, when you look at this number, you realize that this is not as good as your feature engineering. It is actually worse than random forest, but better than decision tree. Once again, this illustrates the no freelance theorem. This problem was not something which brings out the strength of support vector machines. You could do some other problem to bring out this. Now, I'll give you this as an exercise. With the default values of SVM, you see that I'm using very default values for doing the SVM. The model that I get is not that great.
Yes.
Oh, yes.
Somebody is typing.
Yeah, there is a lot of disturbance. Like, yeah.
Please mute yourself.
Somebody else and maybe unmute you.
Yeah.
Yeah.
So you notice that I use the vanilla version of the SVM. SVMs actually traditionally take a lot of tuning. There are a lot of parameters to tune. Guys, somebody please stop typing, or I may have to mute everyone. Okay. This is another nuisance. So if you just check if you're on mute, if you're not on mute, make yourself on mute. And when you feel like speaking, please unmute yourself. Okay, so when we look at this classifier, you notice that I have not done anything special here. There are a lot of parameters that you can play with in a support vector classifier. Remember, there was the budget, the cost. How much cost are you willing to give it? Right? And things like that. There are many, many parameters that you can give. You also remember that you could have used a polynomial kernel because polynomial regression worked for us, right, for the river data set. So you should play with this. You should change this to polynomial. You should try out different things and try out these parameters. I'll give you guys a hint. SVM can outperform all the other models here, but it will need tuning. Okay? I leave that as an exercise for you to play with and try. I've deliberately left it in a vanilla form at which the results are good, but they could be much better. They're not overtly impressive. Remember that the state-of-the-art results you would get is close to 90%, right? 89, 90% accuracy. We are not getting that with SVM in the vanilla form. So this brings out the fact that complex models need a lot of tuning before they start. The hyperparameter tuning is a big deal with them. So we can do that. And in the vanilla form, it's good, but not excellent. So it's worth looking into. So one of the questions that arises, remember I talked about, so this is, by the way, a new thing I'll introduce you to. When you look at the probability or at what probability of it becoming 0 or 1 should you declare it to be either, right? Let's say that the probability of 1 is what? At what point should you put your probability cutoff? Say that if the probability of a point being 0 is greater than, or 1 is greater than what? Should I declare it to be 1, right? The positive test case. So you can do this plot. These are called precision recall curves and discrimination threshold. So what they show you is, you see this red line? This shows how the precision varies as you increase the probability at which you put the cutoff. Right? And recall decreases as you increase the probability at which you put the cutoff. So obviously you want a point at which the sum total of precision and recall, the F1 value achieves a maximum. So you get a very good F1 value. So you notice that the F1 value, which is the harmonic mean of precision and recall, it peaks here, which is why internally the classifier will use that as a threshold for deciding that at this probability, will declare it to be one class versus the other. So it is worth plotting this out to see what the model is doing internally. And the precision recall curve is very similar to the ROC curve, which shows you the recall and precision, right? And a lot of people these days are beginning to prefer the precision recall curve to the ROC curve. Or I guess you can use both. Both of them have value. But you will see this being used more and more. Now, I would like to introduce you to a library called, it is it's called SHAP, S-H-A-P. It deals with the work of a Nobel laureate, Shapley. Shapley got a Nobel Prize for solving one problem. Suppose a team, let's say a cricket players, they win the match, and you want to apportion some reward money based on how much each contributed to winning the match. How would you do that? If you just give everybody equal money, then the guy who didn't contribute much, he would get the same as the captain or the guy who made the most runs. So the question is, how would you distribute an amount of money or amount of rewards, whatever form of rewards, proportionate to contribution? So that problem is quite interesting, and it maps to machine learning in one sense. You can ask this question: if you treat each of the features as a player, at a given point, let's say that given my weight and height and various metrics, various features, which factors are more responsible for me having or not having diabetes, let us say, or heart disease, or any one of the diseases? From a medical perspective, it would be important to know, for example, which is the highest risk factor at this moment for me? Which factor contributes most in pushing me towards diabetes? Which factor contributes most in taking me away from diabetes? That would be worth knowing. And that can be answered by using the analysis that Shapley pioneered. In Python, it exists as a library SHAP. What it gives you is the contribution of each player being each of the features in determining the target variable value, in making the prediction. So you realize that in random forest, we had something called the feature importance. I told you that take it with a grain of salt, don't trust it too much, because for a variety of reasons, it's a very rough and ready measure. Shapley values are much more robust. They have more nuances. They're very in-depth, and they are a part of the effort to do explainable AI or explainable machine learning these days. So at this moment, I just gave an idea of it. It says that the X2 factor is twice as important as X1 factor. You can apply it to SVM because SVMs don't have a feature importance built in. And you can apply this to any kind of model. You can apply it to gradient boosting. You can apply it to deep neural networks. You can apply Shapley to anything you want. Are we together? Now, this is one addition to this. Then, in the California housing also, if you remember, we did all sorts of things in California housing. I will now give you a way of using support vector machines. Now, what is the coefficient R squared and the mean squared error? 0.07. Do we remember what was the mean squared error for random forest? For random forest, our mean squared error was 0.05. So support vector machines in the vanilla form is not doing as good as this, but it's almost as good. The R square is 83%. There it was 78 or 79%. And for linear regression, if you remember, linear regression, the mean squared error was 0.1, and the R squared was 70%. So obviously much worse. So let us see how we apply support vector machines. By the way, before I do that, let me show you how we do feature importance. You can do feature importance using, in the case of a random forest, using the feature importance that comes built into random forest, right? You can also use Shapley. When you use the Shapley library, you get a feature importance, which is pretty much aligned to what the built-in feature importance did. But you can do more than that. You can take a data point and you can say, what are the forces that are influencing it, right? And you realize that the force that is increasing so let's look at this data point. At this data point where the value, the house median value is 1305. Remember that we have taken the natural log of it. And so we have to take the anti-log of this to get it in real numbers. But because we took the log of it, it's 13. So at this point, it says, which is a random point we took in the data, it says that the thing that is decreasing the house price, the factor that is most influential in decreasing the house value is the age of the house. The older the house is, the less it will sell for, the less the value of it. I hope it agrees with common sense. Then, on the other hand, what are the factors that are most contributing to high price of the house? Median income. In other words, affluent neighborhoods where people's incomes are high tend to have expensive homes, which is common sense because only high-income people can afford expensive homes. What is the second most important factor? The second most important factor seems ocean proximity inland, right? If the house is, it turns out that if it is inland, it is not, well, this is very interesting. If it is inland, it has quite a bit of effect on the house price. The next is location. So these are all location. You notice that the three most important factors are location. All of these are location related. Right? And so this is how you see the value of different factors contributing to a house price. Guys, is it easy to understand? It just shows you that for houses which are high value, what are the factors that are increasing the price of the house and what are the factors that are decreasing the price of the house? Right? So clearly, the older the house, it works against the house price. Whereas median income is not really a factor because it's sort of goes hand in hand with people. But all the other factors seem to be location, 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 as real estate people will tell you. Right? These are all location factors that influence the price of a house, which is common sense. So if you take this, this plot is made for one data point, right? One rather expensive house. What Shapley comes out with is something actually quite, there's a very rich visualization, but it needs some interpretation. If you take this plot and you rotate it 90 degrees, and now you say, can I see the contribution at every value of the house? So these are low house prices. So at the low house prices, what is increasing the proximity of the house? It says that what is increasing is ocean proximity inland. So basically, their houses tend to be mostly inland. And the factors that are, if you look at that, house median age. So low house prices, very low house prices are very old homes. Does that make sense? I hope it makes sense, right? On the other hand, if you go here, you realize that let me take a fairly expensive home. Order by value. Let me take it this way. So you can order it by different sort of things, by output value, by, okay, I'll leave it as by similarity. So you look at some other point, the median income, at this particular value, the income begins to matter in certain house price values, whether people there are affluent or not, and so on and so forth, right? So the median income becomes huge. And you notice that at high house prices, most of the factors that matter seems to be related to location factors, longitude, latitude, proximity to ocean, and so on and so forth. So not much in the housing price. Actually, this plot doesn't say anything that is not obvious, but it is a plot worth knowing about. We are going to use this now for support vector machines. Support vector machines, like any complex algorithm, can be used both for regression and classification. Here we are using it for regression. When you use it for regression, I'm just using the vanilla version. I'll leave it to you to use it in a better way. Use it for, let's say, tune the parameters and get better values if you can. But if you use it for regression, then why did I leave it at this value? Because at this value, it will run on your machines in 35 seconds. But once you start tuning it, you'll get better and better model, but the runtime of your model will also go up. It will take quite some time to build. So here we go. We get about 80%, 78.5% coefficient and 0.05. As you know, random forest did better than this, if I remember. The vanilla form of random forest did better than this. Mean squared error was less. The coefficient of determination was 83%, and here it is. What is it here? 83% versus 78%. So obviously, 5% less. Residuals look okay. There seems to be a fairly good correlation between prediction and reality, right? And this needs to, we need to run it for a smaller sample. Anyway, I can run this. It may take some time to run. So SHAP takes quite some time to run. It's something to be aware of. So guys, any questions at this moment? SHAP is a new thing I introduced, but forget SHAP for a moment. Does the syntax of support vector machine look very straightforward? By now, the syntax of scikit-learn should be looking very familiar to all of you, is it?
Yes.
It's looking pretty familiar, right?
Yeah.
Shapely value, right? I just introduce you as a teaser, guys. I don't expect you to understand it fully because I explained this in a different class. It is just introducing you to something that is interesting without giving too much explanation for it. Take it as a fact that it leads to, it somehow gives you more insight into what factors matter compared to just feature importance. So I won't talk about this. Maybe I'll talk about it in a separate session entirely devoted to it. But get used to and then you should use it more often. But today was just a teaser or a sort of introduction to it. Now, one of the things I haven't done is showed you the solutions in R. So today I believe I owe you that. Let me do that. All right, guys. So I'm going to show you the solution of this, everything that we did, but we are going to do it in R now. And it is written out nicely here. So I'll explain. We load the data. So this line number, this should be easy. Line number 4. We are just reading the data. We are splitting the data into test and train data, training data and test data. We attach to data so that X1 and X2, we don't have to keep referring to them again. We look at the structure of the data, which tells us that it's made up of 3 attributes, X1, X2, and T. We summarize the data. You notice that we are taking summary of the data. This is very much equivalent in pandas to what, guys? Can you tell me what was the pandas equivalent?
Describe.
Describe.
Okay. So it is almost a one-to-one equivalent almost everywhere. Here you call it summary, there you call describe. Unique is literally the word. If on pandas column you do unique, you will get essentially the same output. You do the correlation plots. Here is the correlation plot for you. There are only 3 variables, X1, X2, X3. So the correlation plot is not likely to be something very remarkable. Then If you try to do pairwise plot, you will see, you'll get a plot like this. And now in R, you notice that everything is just less code. One line of code gives you summary, but that pandas also gives you a core plot, this, that. As you get used to R, those of you who you will realize that a lot can be achieved in just one liners, one functions, and so forth. Like for example here, pair plots, right? Correlation. Everything is just one liners in R. R is very good for most of the standard machine learning. Though for the newer stuff like deep learning, etc., it has become these days Python first, right? And our libraries are released a few months later, but ultimately they catch this sort of, or a few months later, so they catch up after some time. So if we naively use logistic regression on the river dataset, do you remember that it was a disaster? You can see it. The syntax of R is, the way you write it is, you're saying T depends on everything else, everything other than T. So what is everything other than T? It would be X1 and X2. So R gives you this very sort of a succinct syntax of building models. Do you notice that we don't have to do this explicit separation between the X matrix and the Y, the feature matrix and the Y column vector, input and output vectors? In R, you don't need to do that. It just does it. And of course, if you have done ML100 with me, you have done these labs. So this syntax should be familiar to you from the classifier. I'm just repeating the classifier on this river data set. When you do that, you get, as you would expect, no benefit. Do you see that the model is terrible? The null deviance and the residual deviance are pretty close to each other, which means that the model has not learned anything at all. Right? It gives up. It pretty much doesn't learn. If you try to plot this model and see what is it doing, very much like in Python, it predicts everything belongs to class 1. Right? There is only sand, there is no river. And you can see it because confusion matrix is supposed to be a 2 by 2, but actually one entire column is missing because none of the points they predict as 0 as the river points. If you look at area under the curve, this is the area under the curve, pretty terrible for the naive model. So from that, what do you conclude? You conclude that it's a bad model. Right? It's disappointing. And what is the accuracy? About 60%, but that's the data split. Actually, it's worse than the data split because the data split was more than 60. It was 2/3 to 1/3 or something like that. But here it is 58. So there are times when you can do worse than just majority class. So then we take the more thoughtful approach, the same approach that we took in Python. What do we do first? We take out the river. So how do we do that? This is a very, by the way, in R, the dplyr gives you a beautiful vocabulary. So river, you pass it through this filtering process. You keep only the river points. T is equal to 0. You plot out this, and this is what those points become. Any questions so far, guys? And this is R. And then here in Python, I used polynomial regression, right? Here, I use both actually. First, I tried to do it with the sine wave because somebody said, why not use a sine wave? Well, here we try to fit a sine wave model to it. When we fit a sine wave model, the sine wave model fits pretty well. And after that, as you can see, it fits pretty well. By the way, this part of the exercise, the reason I'm moving a bit fast is because this is essentially a repeat of your ML100. We have done all this in ML100. Do you agree, guys? Do you remember us doing all this?
Yeah.
Yes, we have done this. So it's nothing new. This code should look very, very familiar to you. It is. And so we have a pretty good model. And then you could have used, by the way, in R, I do both sine wave model or polynomial model, just to illustrate that there are many paths to building a good model, many approaches. Once again, the residual plots look good and so forth. And so this is the polynomial model fitting the data. Once you do it, all you have to do is extract out distance from the center of the river, which is the absolute value of the prediction minus x2 minus prediction, distance from the center of the river. Once you do that, you can make a box plot, and in the box plot, you can clearly see river points are here and sand points are further off from the river. Nice. By the way, it's people these days try to get pretty with there. They use the violin plot. Violin plot, if you understand, it's good actually, because it gives you a bell curve distribution over the data. It gives you the, not bell curve, it gives you the kernel density estimation over the data, KDE. KDEs are just, think of them as basically density plots, right, of how the data is spread out. So if you look at that, the simpler version being just this box plot, clearly, you don't even need to build a machine learning model once you do the feature extraction. Common sense says that at distance, x3 is equal to 50, or anyway, 30, 45 or something. You could have made a decision boundary here, isn't it, guys? Separating the yellow from the green, you can make a decision boundary here. Do you see? Do you guys agree?
Yes.
That is it. At a distance of about some 45 or something like that, you already have a decision boundary. I mean, this is the beauty. Sometimes, the problem simplifies so much just through feature engineering that you don't have to build a model. But of course, we'll go ahead and build a model. Now, when we build again a logistic model, do you realize what a huge difference there is in the change in deviance, residual deviance? Residual deviance has come much, much lower here. And you can see that the p-values are good, pretty good here. Standard errors, the z-value, the estimate divided by standard error, the ratios are also pretty good. All those points that we mentioned we should observe are pretty good. And this time around, do you notice that you get a proper confusion matrix, a confusion matrix which has the 2 rows and 2 columns. Principal diagonal has most of the points, off diagonal has fewer points. If you look at the accuracy of this model, it's 91.25%. It means that the model is doing very, very well, right? When you take this model, it's doing very well. Again, guys, this code is what we have been using for classifiers all along. Huh? And that's that. Right. That sorry guys, I woke up very early today. So when you look at the ROC curve, do you guys see this ROC curve here? Where my mouse is? Would you say that this ROC curve is really impressive, isn't it?
Very much.
Yeah. Very much. It's just like we did it in Python, of course, is the same. And the area under the curve is 98% approximately, AUROC. Again, very impressive. So you know that you have hit the nail on the head. Right? You have a very, very good model. And that's the point of feature engineering that I wanted to show you with us. Same thing we can do with the flag data set. So I will read out actually this conclusion because I've written it out in the book form. The burden of the river dataset analysis was the importance of a thoughtful, methodical approach to data. We learned that considerable time and effort should be invested in feature engineering. Doing so leads to learning the kinds of classification models that are radically more effective than a naive, hurried approach of blindly applying algorithms to data. There was yet another lesson in this exercise. Note how a judicious use of nonlinear regression or polynomial regression facilitated the process of feature extraction. Without it, the linear classifiers were not much use. This is a generalizable observation. Rarely do real-world problems come in such a way that it can be fruitfully attacked with just a single approach and a single algorithm within that approach. Many approaches and their algorithms collectively come together as midwives to bring forth the best model and effective predictions. The magic is in this conspiracy of many ideas. And that's something you should remember, guys, that whenever you have built a model you're proud of, there's some thing that is making really good predictions, It is like an onion. If you peel the onion, you'll see layers and layers of things you have done to reach that high level of model accuracy and things like that, goodness of the model. So that was the main lesson here. We can repeat the same thing with the flag data set. When we do that, no harm. Once again, naive approaches lead to disaster. Right? We can use the quadratic discriminant analysis. Also, doesn't take us anywhere. But if you do feature extraction, distance from the center of the river, very clearly in this plot, you can literally hand draw the decision boundaries in terms of distance from the river. And so you expect that if you build a classifier, it would be very accurate. And indeed, it is very accurate. You have 85% accuracy. Right? You can see that the error rate is almost 84.3. And the accuracy is, and error rate is 15.6, which is the opposite of accuracy. 1 minus accuracy is the error rate. Right? So pretty good model. Right? You can build with this. And pretty much you can try any of the linear models, logistic regression, linear discriminant analysis, quadratic discriminant analysis. I guess, guys, you must be remembering these things, LDA, QDA from our last ML100 class. You can apply any one of those and it would work. Now, Hill dataset, I haven't given you the analysis and I kept it off. This is part of your homework. I will probably not show you the solution, but the basic point is that it works like a charm. Feature engineering works very well on the Hill dataset. If it is any hint to you, this is how the Hill dataset looks if you visualize it. I'm going to release it to you guys. See, guys, if you can build a regression model for it. Are we together, guys? So today, actually, I'll teach you guys a new topic called, which uses the kernel. We learned about the support vector machines. There were one application of the kernel. Today, I'm going to teach you another application of the kernel. And this would also be a good point to teach neighborhood-based algorithms, algorithms that rely on neighborhood methods. But for that, I would switch over to the writing pad and therefore to the other machine, and I'll explain it there. But before I do that, guys, I'll take any questions. Anybody has any questions?
Sir, will you share even the R solutions with us?
Oh, yes, of course.
Okay.
I will share, of course, I'll share all of these, right? But obviously, please don't share it any further. Keep it within the class.
Okay.
I'll share it, of course. Good thing with R is I actually wrote it out properly with explanations. The Python one, I still have to add all of these explanations to. But
Asif, you're talking about that book. Is this that book?
this is that book, exactly.
Okay.
Do you like it?
Yeah, this is nice. It's nice. The contents on the left-hand side.
Yes.
Yeah. And whatever you speak, right, all those nuggets of wisdoms are also there embedded. That's
It
good.
is there in the book, yes. So guys, give me a minute. I'll go have a glass of water, come back, and we'll continue from there. Would that be okay, guys?
Sure.
I'm feeling a bit thirsty today.
Yes, of course.
I'll stop the recording. Give me a moment, guys. And 8. So all right, all right, guys, can you see my screen?
Yes.
Yes.
Perfect. So we'll start from here. This is where we stopped yesterday. We were talking about
Can
vector.
we start recording?
Oh, yes, my goodness, I must. I stopped it, isn't it? So where's the recording control? So the topic today is a new topic actually that is related. Oh, this thing came to the screen. One second. Do you guys remember this discussion, guys? We stopped yesterday by saying that support vector machines or kernels, they help you find the lighthouses that can guide you along a non-linear decision boundary. Right? These lighthouses are your support vectors. That is, and so SVM is a clever technology, clever algorithm that can find the lighthouses that can help you navigate the decision boundary or find the decision boundary. It helps you flow a river through the data, the widest river that you have. So today's topic will be a different topic. Actually, maybe I should start with a different page. I can share all of these pages with you. Today's topic will be neighborhood methods. So neighborhood methods are quite interesting and remarkably simple. The intuition is the obvious. The intuition is you are defined by the company you keep. In every culture, people tell you that if you want to judge a person, go look at the friends of the person. And the friends give you a pretty good idea of what a person really is. The same is true in machine learning, and the intuition translates in a very obvious way. So suppose you look at the space of cows and ducks. You're looking at a space in which the features are, once again, let us say that the features are weight. This is your x1, weight, and x2 is the size. Would you agree that most of the ducks would be, let me take a slightly, let me take something like this. So most of the ducks would be, data points would be like this, and most of the cow data points, let us say, would be, what should I do for a cow? All colors, let's say cow. Okay. So most of the cow data points would be together. They would be big and heavy creatures. Would you agree with that intuition? Isn't it?
Yes.
Guys, is any feedback? Is this pretty obvious, right? In the weight and size space, the cows will be big and heavy, and the ducks would be rather light. This would be the ducks. This would be the cows.
Right.
Make sense, guys?
Yes.
Yeah. So now what we can do, what this algorithm gives you a hint that, suppose I give you a point. Let's take a point, X. Without knowing any machine learning, what would you say that point X? You get an animal whose weight is given by the point at A, the point A. What would be your guess? What animal is it? Is it a cow or a duck?
Moo.
Guys, what would it be? A point at A, you find an animal which is big and heavy. Would you guess it's a cow or it's a duck?
Oh,
Cow.
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 I think some said moo. Good. That means cow.
I'm sorry. Say that again.
A cow. I think previously somebody made a cow noise. Something like that.
Right. Okay. Yes. So it is a cow. And what made you say that it is a cow? If you think a little bit about it, you would say that, animals whose weights are similar, neighboring, if you look at this point and you look at its neighborhood, look at the neighborhood of a point. Neighborhood of A is mostly cows. In fact, here it seems to be completely cows, isn't it? The data points that you have, all the animals that you have measured in the whose weight and whose size are similar to A's or close to A's, they are all cows. So, and on the other hand, if you get a point like this, B, a point B, once again, if you look at the neighborhood of B, the neighborhood of B are all ducks, isn't it, guys? And
Yeah.
so we come to a basic intuition. We say that if the following conditions can be fulfilled, which are no-brainer conditions, if we have a notion of distance in the feature space, what is the feature space? Feature space X, right? So see, X belongs to some dimensional. Here it is two-dimensional, but let us say d-dimensional space, right? This is your feature space, right? So by the way, this is a belongs to symbol. X is an input vector. You remember that. Any input vector is a vector in the d-dimensional feature space. If you can define a notion of distance, actually, let me not use the word D because D stands for distance. It will start getting confusing. It is N. Let me just say N dimension. N is often the number of points. Well, I don't know what should do. Let us say P dimensional space, R to the power P. So suppose you have a P dimensional space, feature space, into which the X vectors exist. Now, this is implicit because when you talk of neighbors, you assume a notion of distance. You can't have a notion of distance. I mean, you can't have a notion of neighbors where you can't define distance. Now, you may wonder, is that even possible? It is possible. For example, if you're talking about cats and dogs and pigeons, and let's say that one of your columns in the data is like that. It is the species of animal. Well, here we are trying to predict the species of animal. I wouldn't take that. Let's say color of the animal. If you're looking at the color of the animal, what is the distance between a blue and a green? It's not defined unless you're looking at the wavelength of light. And let's say we don't. Then there is no well-defined notion of green green animals versus blue animals or whatever it is and so forth, or bluebirds and so forth. So not all spaces, not all feature spaces support the notion of distance. You're lucky when you have a notion of distance. That also brings up an interesting topic. What is distance? So let me pose this question. What is distance? Would somebody like to venture a guess? What is distance? What is the distance between 2 points? Let us say you have 2 points. Two points in the feature space, x prime, in the feature space, RP, then what is a good notion of distance? What is the distance between x and x prime? Anybody would like to say?
The subtraction of the x-axis square plus subtraction of y-axis square root. The
Yeah.
Pythagorean distance.
Yeah, so one easy notion of distance is you can say distance between x and x prime, right? And let me use this as a Euclidean distance. Euclidean distance is distance between these 2 points is xi minus xi prime, that is component wise squared, right? So x1, x2, x1 of the first one plus x2 minus x2 prime, if it is 2-dimensional space, square root. Would you agree that this is your Euclidean distance? Right? So between 2 points. So for example, if this point and this point are x and x prime, this is x1 minus or rather x prime minus x1, right? And this is x2 prime minus x2, right? And so here also I could write it the other way around, it doesn't matter. And so this distance from here to there by Pythagoras theorem is the square root of this. Are we making sense, guys? So far so good, guys. Is this obvious?
Yes.
Yes, good.
So this is called, in more formal terms, it's called the L2 measure, and I'll explain why. If you generalize this concept, you can talk of the Manhattan distance. Manhattan distance is as a taxi driver goes, or as I suppose modern day, one of these Uber or Lyft would go. See, if you are in a street, in a city, let us say that the Manhattan, for example, is laid on a grid, right? So suppose you are at this point x1, x point, x here, and you want to go to the point x prime. How would a taxi driver go? The taxi driver cannot just jump through the buildings or drive through the buildings. The taxi driver would be forced to go like
The
this,
edges. Yeah,
isn't it?
the edges. Yep.
Right? Whereas the way a bird flies could be, would be like this. So let me write this down. Flies. And this one would be taxi driver's path. Now, interestingly, what is the taxi driver's path? If you think about it, it is the absolute value of what is this? This is x prime minus x, the size of the magnitude of it, right? And this is the x1 part of it. This is x prime x2 minus x2. the absolute value, right? So you would say that the Manhattan distance or the taxi driver distance between x prime is equal to x prime minus x absolute value plus the first component and the second component, the absolute value. Does this make sense, guys? Is this obvious what I'm saying?
Yes.
Yes.
It is obvious. So we realize that, distance depends upon the situation. Now, one easy way to generalize this distance is to write is to write this expression, which is called the Minkowski distance. The Minkowski distance between 2 points is defined as distance of between x and x prime of dimension, let us say dimension of measure n, m, let's say m, is given by this interesting expression, x prime 1 minus x absolute value to the power m plus x2 prime minus x2 to the power m. And you can go to as many things as you want, and you take the mth square root of it. So this is an interesting expression. Let us break it up and see what it is trying to tell us. When m is equal to 1, then d1 of x prime becomes the 1th square root of the square root is the 1 itself, right? So this just becomes to the power 1 here. 1 I need not write, isn't it, guys? So this is this plus x2 prime minus x2 absolute value. So what does this look like? Is it the same as this guy here?
Yeah, Manhattan distance.
So when m is equal to 1, it is essentially Manhattan distance. On the other hand, let's see what d is equal to 2 becomes. Oh, sorry, m is equal to 2. The second, and the word people use is the norm, the second norm. So we have x1 prime minus x1 absolute value squared plus x2 minus x prime x2, sorry, minus x2 absolute value square root, isn't it? The half is implicit here. What does this look like, guys? Is this the
Euclidean.
same as the Euclidean distance?
Yeah.
Euclidean distance. Now you realize that this is remarkable. So we have generalized it. You can now go to D3, D4, isn't it? You can even go D infinity.
Asif, can I interrupt? Asif?
Sure, definitely.
For the Euclidean distance, you're squaring it anyway. So why do we need to take absolute value?
No, it is just I'm just saying that you do it because it's a generalized, the Minkowski distance is defined like this. Right?
Yeah, that I get it.
But in reality, what you do is for
Okay.
even powers, you don't need to
Okay.
take the absolute
Okay,
value at all.
generalization. Got it. It's just a special case. Got it.
It's just a special case. But in reality, of course, for even powers, you would realize that it's pointless to bother taking the absolute value.
Yes.
Negative to the
Right.
even power would be positive anyway. But now comes something very interesting, guys. Can you imagine? Now you can have a notion of D infinity distance. What would it be?
0.
No, it's very interesting actually. So what will happen is, suppose 2 points are like this, right? And this value So can I just for brevity use the word delta
So is it 1?
delta x1 to be x prime minus x1 prime minus x1? Can I write it like this, guys? So this is the first delta x1 and this is delta x2, isn't it? Suppose by definition I create a new notation. Yes. So you realize that what will happen is when you take this d, a large number, m is equal to, let's say, 100. I'll just take an example, or even let's forget it. Let's take 10. Let us say that, for example's sake, this seems to be about 4 times this. Or is it true? Or maybe 6 times this. Let us say that here, does this look approximately true here, guys, in this figure?
Yes.
Right. So what will happen is, if you look at the M10, you're saying delta x1, right, to the power 10 plus delta x2 to the power 10, the whole thing 1/10 power, right? And see something beautiful that happens. Now I'm going to do a little bit of a magic here. What I'm going to do is I'm going to write it like this. Suppose I took delta x1 out, x1 to the power 10 and to the power 1/10, which is nothing but delta. And this equation therefore becomes delta x2 over delta x1 to the power 10. 1/10. Does this make sense, guys?
Yeah.
Right? And this one would be delta x1 times 1 plus, now delta x2 is smaller than delta x1. In this case, let us say 1/6. What is 1/6 to the power 10?
It's a lot. I mean, to the power of 4 itself is 1/1296. So it's kind of approaches 0.
So you realize,
6 raised to
1/6 raised to 2.
1/6.
no, it can't be 1/6. 1/6 to the power 10th is approximately 0.
Yeah, it approaches
Try it
0.
out. Okay, you want to try it out on a calculator? Let's do that.
Will it approach to E? When it
No,
goes
no.
infinity?
It will be infinite or no?
No, we will do that. Let's do this, guys. Huh? Let us do this. We are saying, where is it? Does it have a sign?
Oh, it's 6. So it's 6 times 10, right?
The
6 raised to
6
10.
growing in the denominator, right? The denominator is getting bigger and bigger.
So
1
1
divided by 6 to the power 10.
divided by 6 is equal to 0.16, right? 0.1666.
Yeah.
Is there a sense of power here in this Windows? I'm not very.
X to the power no.
I think you have to change it
No,
to a
you'll have to
different
multiply.
MS. What is MS?
You end up not moving.
Scientific?
Square it 2 times, then multiply it,
Yeah.
divide by 6 again,
Oh goodness, that's okay.
and again.
Didn't you have a scientific calculator in Windows? Doesn't exist. Huh? Oh,
Do it on the iPhone.
Square it 5 times, sir.
Yeah.
square it. Yeah. Okay, I could do that.
But anyway, this is close to 0. You're right.
Yeah.
Yeah.
This will be close to 0 actually. Yeah.
As if I got it. Yeah. So,
You guys got it, huh?
Yeah.
So you'll realize that this number is very close to 0. Like, okay, let me do that. Yeah. I opened up the R. So x is equal to 1 by 6.0. Right? What is x? This x to the power x.
That's 1.6 to the -8.
Sorry, x to the power
10, sir, 10.
yeah.
Yes, this is it.
It's
What is it? 2.14
134.
power minus 5. So it is 0.0000002.
0.02.
So it's a very, very small number. Would you agree? On the other hand, if it is, by the way, this is only to the power 6. If I were to do it to the power 10.
10, yeah. It
What
comes
is
to 1.214 to the power of -8, 10 to the power of -8.
Exactly.
1.65 to the -8, just
Yeah,
like you
power
showed.
minus.
Yes.
So would you all agree that if I were to give you as salary 1.65 to 10 to the -8, you would be rather unimpressed, right?
I would rather not take it.
Yes, exactly. So it's like that. You got nothing essentially, right? So that's the intuition. Now let's go back to that. What we are trying to say is that this is approximately 0, isn't it? This term is approximately 0. And so what happens? If this term cancels out, you're just left with x1.
Yeah.
1 to the power 1/10 is just 1.
1.
And so this is approximately 1. So what is it saying? By 10, already the meaning is obvious. By the time you go to 100, what will happen? Once again, this will remain, isn't it?
Yeah.
And so think about it. As d, you realize that d, this is approximately equal to this. D100 would be even more better approximation to just delta x1. And so d infinity is essentially equal to the biggest distance. Whichever axis has the biggest distance will matter, right?
So the difference gets amplified.
Yes. So what happens is that the infinite norm just picks up whichever distance along the axis is the biggest one. All others go to 0, and that is the only one that survives, isn't it? So what is it? It is actually finding this of all the delta x1, delta x2, delta x, let's say it's p-dimensional data, then it is picking what? It is just picking the max of them. Does this make sense, guys? The maximum distance along the axis. D infinity is just this. It picks up the max. So this is a very powerful concept, and the person who discovered it is, or to whom it is attributed, rather, is Minkowski. Minkowski, by the way, was very influential in creating the whole theory and a bit of the mathematics that would later on go into the special theory of relativity. So, well, this is it. This is the notion of distance. So you say, well, that is getting pretty interesting mathematics now. What is its relationship to machine learning? Well, machine learning. Go ahead, Aditya.
Just a trivia. So I've heard that Minkowski is probably Einstein's PhD advisor.
Minkowski was Einstein's PhD advisor. Maybe true, actually. I'll have to look up. That's a very good question. I don't remember his PhD advisor, but quite likely, could be. Yeah. And a wonderful mathematician, by the way. The Minkowski space, the four-dimensional space in which special theory of relativity lives. The space-time is Minkowski.
Yeah.
So now, all right. We will now continue from there. And we say that, can we do more generalizations? And so you can ask yourself, what is the distance between two words? You could easily ask that question, right? So there are many ways that you can come up with the notion of distance, for example, right? So some of these ways are quite interesting, actually. We will go into, when you look at machine learning, you find that people define their own, very carefully define the distance between two vectors, their input vectors. And that often is their secret sauce. They will guard their definition of distance sometimes because it gives them that extra bit of performance because they did something pretty clever in doing it. So that raises the question, what is distance? What is a more broad definition of distance? And the definition of distance is the following. Broadly, a distance, a metric is, and the word people often use is metric also. Anyway, I'll use the word metric, but metric is not exactly what it is. A theoretical physicist like me would frown upon that. You'll say metric is more like G mu. Forget about what that is. Distance is something that has the following properties. distance between 2 points, x and y, and now I'll use the word x and y, or maybe let me just use x and x prime. X prime is always greater than and equal to 0. In other words, it's a positive definite quantity. Does that make sense? Distances are always positive, right?
Yeah.
Right? Makes sense. The other thing that it says is that if distance x and x prime is equal to 0, if distance, it implies, bidirectionally, it implies that x is x prime. They're both the same points.
Yeah.
This also makes sense, right? If you don't have to go even a little bit to reach the other point, it means that that other point is where you are.
Both are curves.
Yeah. And the third is, and the third thing that comes in here is something which is also pretty obvious. See, if you have suppose this is a point x, and maybe actually x, and this is a point x prime in whatever space, would you agree that the distance is always the shortest path, right? By definition, let us define is the shortest path. And the formal term mathematicians use is geodesic. Right, this is now, where does the word geodesic come from? Geodesic people like me who do differential geometry and so forth.
Differential geometry.
Is the intuition comes from geo. Geo usually stands for the earth. So imagine a globe in your hand. Right? Now look at this. What is the shortest path from here to, let's say, Europe, London, or to, let's say, India? The shortest path you could claim is that you could burrow through the center of the earth and come out the other end.
Yeah.
Isn't it?
Yeah.
So that would be 6,400 times 6,000 times 2. The radius of the earth is 6,400 kilometers. So 12,000 something kilometers later, you would be on the other side. Right? But you know that if you take a flight from here to, let's say, India, you go more like, if I'm right, about 13,000 miles, which is more like 20,000 kilometers, isn't it? So where did that extra distance come from? Well, it comes from the fact that you don't burrow through the center of the earth. Right? You instead fly over the surface of the earth, right? Yeah. So when you have the earth, you can go from here to here, not this path, but you have to go this path around the earth. Isn't that obvious, guys?
Yeah.
And this path on the surface is the shortest path. Right? You could do this, you could go the polar route, right? Whichever way you go, let us assume that the earth is one big round, which is it's not really true, but it's sort of a ellipsoidal slightly. But assuming it was a sphere, you would have to go along one of the arcs, along the surface. So that is the shortest path, geodesic, the path along the geo. So the word geodesic has stayed. It is used more formally in mathematics to represent the shortest distance between 2 points. Here, in this situation, you would agree that the shortest distance between this is this, right? This is dx x prime. But suppose you take any other point in this space that is not on this line. Let us say that you take a point y. Would you agree that, or any y, let me just take it here. I don't want it to look like a triangle. Let's say even this y. Or z. Would you agree that d x y plus d y x prime will always be greater than or equal to dx x prime. So this is z, and I could take another point, w here, right? So if it is w, you realize that these two, x to w and then w to x prime, would equal this distance, right? In that situation. But in all other situations, this inequality will hold for any y value, whether y is here or it is z or it is w. Will this thing hold?
Yeah.
Right. So it is a case, actually, it's sort of related to something like Schwartz SC, actually, Schwartz inequality, but it's common sense. So we say that any function that satisfies in a space that satisfies these properties is a bona fide definition of distance. You can just conjure up any kind of function that fulfills these three properties. If it fulfills these three properties for all points in the space, it is a distance measure. Are we together, guys?
Yeah.
Right. That is a distance. So you say, well, that's taking a deep dive into what a distance is. For once, you should know that, guys. Distances, or definition of distances and similarities, are at the heart of machine learning in many ways. And today we'll see what we can do with distance. See, we assume distance because we always think Euclidean space, three-dimensional space. But data exists in higher dimensional spaces. We need to have a clear definition of distance. So this is it. So I'll just summarize these three criteria. What were the other two criteria? This dx x prime is greater than or equal to 0, isn't it? And a dx x prime is equal to 0 implies, or the mathematical word people use is, I don't know if you're familiar with it, IFF. It's a misspelled if. If it also is represented with this bijective reasoning, sort of. It means x and x prime are the same point. Okay. So these are your basic notions. Any function that fulfills this is a notion of distance. So now let's come back to our cows and ducks all over again. Might as well redraw the cows and ducks because they're way up there. I'll redraw this. Let's take this example. And now I'll start introducing more animals here. These are ducks. Right? These are cows. Oh, sorry. What just happened? Okay. These are cows. Then let's bring in some other animals. Let's bring in, let me have some big ducks. What is close to a duck? Think of a bird that's close to a duck.
Swan.
Swans. Okay, let's bring in some swans now. Let's give them a nice, well, swans are elegant creatures. We better give them a nice color. What color should we give swans? Let's try, well, I'll just give them pink because I can't think of a color at this moment. Let's say that these are swans. Swans are bigger. Are they bigger, guys? They're bigger than...
A little bit, yeah.
Mostly flamingo, pink color.
Yeah. So some small swans can be confused for a duck, isn't it?
Yeah.
I suppose that was the story of the ugly duckling. So here we go. And so now comes this interesting question. And what's close to a cow?
Buffalo.
Donkey,
Buffalo.
donkey,
Let's have a
buffalo,
buffalo too. And I'll represent a buffalo with, what should we do for buffalo? Let's try this color for buffalo.
Mm.
Buffaloes are even bigger, isn't it?
Yeah.
Okay, so, well, they seem to be going along a diagonal. Let's take something that is, let's give these names to that: weight and size. Something that is big in size but not very heavy. Let's say giraffe. Or would giraffe do or zebra do? I don't know if they're close to the weight of a cow.
Zebra maybe, but giraffe are too big.
Giraffe are too big. All right, we'll go. By the way, something about giraffe I learned just yesterday from my kids. Giraffe is the only animal that mammal that cannot speak, that has no vocal cords. It's always silent.
Yeah, I can imagine such a long neck, right?
Yeah. So there we go. So let's say that we take zebra and we'll give zebra a color like this. Zebras are big, but not are, what do we say? Well, they're not bigger than cows. Or we'll take giraffe. Okay. Giraffes are, let us pretend that they're not heavy. So any biologist who's here, please don't get insulted at my lack of understanding here. So we'll pretend that these are. So let's give names to these. And we'll call, these are mostly ducks. And these are swan. These are cows. And these are giraffe. Giraffes. Are we together? So now let's ask ourselves, how can we tell whether something, using the notion of distance, how can we tell whether something is a cow, duck, giraffe, or swan? Easy. Suppose I give you a point like this. Let me take some points. A, B, C, D. You could say that A, B, C, and D, they are, what are they? You could identify. Let's go with A. What would you call A?
Swan.
Swan. And to make a decision, you just look at the neighbor. But the question is, how many neighbors do you look at? You could look at any one neighbor, two neighbor, three neighbor. In all these cases, you would get a fairly good answer, isn't it? But suppose you look at a point, this guy. Let me call it A prime. What about A prime? Is it a duck or is it a swan?
Really swan.
It's a little hard to tell because the nearest neighbor seems to be, or especially if you, let me do this.
Both.
Let me go back and bring those points. What was that dot that I did? Okay. No.
Almost on the decision boundary.
Yeah, it's too close to the decision boundary. So if I take a point, let me make it deliberately very confusing for you. This point, A prime. What is A prime?
Difficult to say.
It's a bit difficult to say. When you take K is equal to 1, the nearest neighbor. So K is the number of neighbors we will use to decide it. Nearest neighbor. Then K is equal to 1. It is a duck. But if you take K is equal to, let us say 5. Now what happens? See, if I make a little circle around this, then what happens to A?
Yeah, it's most probably swan.
Yeah, the majority of the animals around it are swans. Do you see that, guys? There are only 2 ducks. But in a circle around A prime, the rest of them seem to be swans, like 1, 2, 3, yeah. 2 ducks. 2 ducks. Actually, let me make it 6. K is equal to 6. 4 swan. Right? So now, what would you say? Which is the majority? Your intuition will go and say that this is a swan, right? So your answer depends on how many neighbors you look at. When there is overlap, the number of neighbors matters. Are we together? But how many neighbors is too many? Suppose you take k is equal to, at this point, k is equal to, let me take a number, 50 or 100. And to give you the situation, give you a sense of what's wrong with that, what happens is, suppose you are in a world filled with giraffes. Most of the data points in this is giraffes, right? Like this. So then what will happen? If you take the majority, then what is A? You would realize that the majority, if K or something large, then what will this thing look like? If you take the majority, you will get something like 10 swan. Let us say that these look like about 20 points. So you will say you have 20 ducks, maybe 25 swans, maybe you have 30 cows, and you have let's say 50 or 55 giraffe. Suppose this is the count, right? So what happens to you? You have 30 plus 80, 110, right? So if you look at k is equal to 100, what do you think you'll end up with? What will be your majority? Imagine that you go at k is equal to 100, you will end up taking a circle like this. In this big circle, you have to go really far to find 100 neighbors. And what will be the majority here, guys?
Giraffes?
Giraffes, exactly. So you will end up concluding that A prime must be a giraffe. So when you look at this, what does your intuition tell you? There are three different answers based on how many neighbors you take. A prime, what does it really look to you like? If you had to guess, what would you say it is?
Swan.
You would say either a swan or a duck, but much more likely to be a swan. You would like to go with the swan. So what happened? Your answer went from a duck to a swan to a giraffe. Right? So it went from a mistake to what is probably the right answer to again a mistake. So this is an important lesson. The k is equal to the hyperparameter determines the accuracy of your predictions. Isn't it? So how would you do that? So therefore, you set up the value of the hyperparameter by this means. You would first divide the data into training and test, and let the divide data or training data further if you want. Divide training data. So you know that you have first divided data into a training or learning set. This is the test data, right? Now the data that you use for training, you further divide. There are many methods of cross-validation. This process is called cross-validation. I must have taught you at some point, but if not, I'll just at this moment give you an overtly simplified version. What you do is you keep some data from the learning data itself, you hide it, you call it the validation set. And you just give this data to train. And once you train that, you look for that model, that value of K, which gives you the best prediction, most accurate, that value of K, that gives the most accurate prediction on validation set. And of course, later on the test set. Does this make sense, guys? What you do is, while learning, you keep some data aside. And you use that data to validate which value of K. You keep on increasing the value of K from 1 to 2 to 3 to 4. And so what will happen is, you will get a curve. Your accuracy for values of K will go like that. Let's say that your accuracy is this. It will go something like this. You will get to a good accuracy number, which is your best K. Does this make sense, guys? Right? Like, for example, if you take K too high, 100 animals, 100 neighbors, it will become bad. Right? This is actually your classic bias variance trade-off, and I'll explain that to you in a moment. Huh? But let me bring home the intuition. See, guys, suppose I want to know what your political views are. I could go to one of your neighbors and ask, but it's dangerous because that neighbor may happen to have a view that is exactly opposite to your view. But suppose I take a few more neighbors, 10, 15 neighbors here, you would get a pretty accurate estimate. But if I start looking at 50 or 60 million users, I might have to go all the way to Montana, isn't it, to find a neighbor there. And obviously a neighbor there, the people there may not reflect your viewpoint. Like Californians and people in Montana or Wyoming, they tend to have almost diametrically opposite political views. So they are not representative of you. So that is the danger of taking K too large. Danger of taking K too small is, just by accident, you may get wrong answers because your nearest neighbor may be the opposite of you. Do you see the difference, guys? So there is an optimal K in the range, and you need to find what that K is. And you do that through cross-validation. Now comes an interesting point. Suppose you have a space Suppose data has the notion of distance, has distance easily defined. You realize that this approach, and by the way, this approach is called K nearest neighbor algorithm. It is based on simple notion that a thing is defined by its neighbors in the feature space, whatever neighboring thing we have. So it is a very simple algorithm. You're not building a logistic model. In fact, there is no model building at all. It's a completely non-parametric model. In other words, there's no learning. This algorithm is just quiet. It says, I don't need to learn anything. I just need to look at the neighbors and determine the answer. So when you look at K nearest neighbor, and you have a notion of distance, obviously, then I should be able to apply that. So why is this method not universally applied? Like, it's so easy. Why do the rest of machine learning at all? In every situation where the notion of distance exists, let us just go use that. So I'm giving it to you guys as a puzzle. Why would you not do this?
No free lunch theorem. Doesn't always help.
Come again, Kate?
No free lunch theorem. It's not always the best fit for the data.
Not always the best fit for the data. That may be true. Yes. I mean, sometimes.
Maybe to do with the shape of the data.
Yeah, the type.
Works well with the like spherical or something.
dimensions of the data.
Little bit of
If
it. You're getting
Can you
close.
repeat the question?
Dimension is the word. See, what happens is
Curse of dimensionality.
Curse of dimensionality.
Exactly. So let me go to the curse of dimensionality. So I'll talk about, because most data is high dimensional, and high dimensions suffer from a curse, which is sort of one of the worst curses you find in the Harry Potter novels. Right? I remember reading the Harry Potter novels, and there were all of these peculiar curses that could be put on you, and you would be in great pain after that. So it's somewhat like that. One of the most painful things in this space is the curse of dimensionality. It sort of punctures your balloon of optimism. So in this, that oh goodness, that's quite a word, dimensionality. What in the world is this? But before I go to this, I'll give you guys an example. I'll give you guys an illustrative example to pin the idea of k nearest neighbors into your mind. See, when k nearest neighbor, right, is based on training data, you find neighbors in the training data. If you have a lot of neighbors, if you have a lot of training data, huge amounts of training data, then neighboring to a point, you'll find a lot of other points. In fact, if you're very lucky, you might find that the point you're predicting for is there in the training data itself. There is no learning to do. You just look up the value and return it. So which is pretty much degenerates to a dictionary situation. So suppose you know the value for every point in the feature space that could be asked as a prediction for. You just look it up in the dictionary. You're done. It's called dictionary-based learning. It's no learning at all. And it happens, if you remember, you all must have gone through schools and colleges. And again, take this with a huge grain of salt. This is just saying something to pin the idea into your mind. But somebody, I think it was Will Durant, who once said, that education is entirely wasted on the young. Right? Why? Because the young people go to school and college, and the last thing they want to do is learn anything. They're much more interested in having fun. Right? So you like parents think they're sending their kids to college for education. The kids think they're going to college for a party, right? To have the best time of their life and to party around and so forth. And so the universities, they scare the kids somehow into the classes by the carrot and stick of grades and throwing them out of the college if they don't have good grades, taking away their scholarship and so forth. And so kids study. Well, obviously they are highly motivated kids. They are a minority, but most kids are highly motivated by grade and so on and so forth. So they study, right? So the kids don't want to study. The colleges want them to study and so forth. Right? That's how it goes. So one of the things you do when you don't want to study and you want a good grade in the exam is quite often you maintain a question bank. What sort of questions a professor is used to giving, right? And many professors are lazy. They'll keep repeating the same questions. They will have a set of about 30, 40 questions, say 100 questions. And every year they'll take a sample of those questions and ask, right? So, or they'll just change the numbers and then they'll ask the same question, but the answers will be different because numbers have changed. So one of the things people often do is they don't really understand the subject. They would just study well how to solve those problems, all the steps needed to solve the problems, and they would memorize it so that when a problem comes, they would just go through the formula and solve it. Then quite often, if the numbers are slightly changed, what does it mean? The problem is not exactly what you have memorized, but it's close to it. If it is close to it, you make the little bit of a journey up to a solution that you know. So you use essentially a nearest neighbor approach to solve problems in exams, because any new question you get, you try to map it to the nearest problem that you have sort of studied or memorized, or if you're allowed cheat sheets, you have a cheat sheet for. Does that resonate with anybody?
Yes.
Yeah.
Yes, it does, right? So
Yes.
this is it. That's your k nearest neighbor, essentially. Right? you find similar things for whom you know the answer, and you
Non-disclosure agreement.
non-disclosure. Yeah, of course. I should pose the question the other way around. Is there anybody who has not used this at some point in their life?
Yeah.
Right. So that is that. So that's the basic intuition of nearest neighbor. Anyway, I thought I'll take a digression. So now let's come to this question of dimensionality and what is it? And that would be something I'll talk about. See, dimensionality is a very interesting thing. Before I go to that, let me bring back an intuition. You know, Bay Area is densely populated, isn't it? We live in, most of us spend our lives in these row homes, right? Track homes, in which these are cookie cutter homes. If you look at your house structure, 10 different neighbors will have exactly, or more will have exactly the same structure of the house. Really is your house very unique. And all these homes are very close to each other. Joke is that you can just, if you want to exchange a book, you don't have to go to the neighbor's house. You can do an exchange through the window, isn't it? So, well, if you want, let's say, K nearest neighbor to know your views, you can even take K is equal to, be generous, let's say K is equal to 20. And 20 neighbors around you are very easy to find, right? Within a couple of 2-3 minutes of walk, all those neighbors are there. Is that true of us, guys? Or at least within 5 minutes, all our neighbors are there, 3-4 minutes. To reach a total of 20, the furthest neighbor to reach that would not take more than 3-4 minutes, right? For most of us, right? Unless you live in a palatial place up in the mountains. Whereas, suppose you were to go to Montana or Wyoming or something like that, and you're out there in those homes, cottages. If I say, let's go find 20 neighbors, it would be quite a distance, you know. For example, when you go to meet your neighbor there, you get into a car and you drive a substantive distance through ranches and forests and whatnot before you reach your nearest neighbor. Anybody who has been to those states, would you agree?
I lived in Montana for 5 years.
You did? Would you agree with that?
Yes, certainly, yeah. I lived in a university town, so that's
there,
what I've seen places like that.
Yes, exactly.
1 person per square mile, that's a density.
That's pretty much it, yes. So what happens, guys, is that if you have to go for 20 neighbors and you have to go very, very far and maybe cross the state boundary along the way, those neighbors are not really representative of you, right? So for example, if I want to find how much snow has fallen outside your house, and I have to take the average of the snowfall around the houses of 20 of your neighbors, you may realize that that would may be very, very inaccurate, because snow may have fallen heavily in you and your nearest neighbor's house, and your other 18, 19 neighbors may be so far away that there was no snowstorm there, right? So it's not representative. The further off you go in the distance, the less representative they are of your local context, right? And so factors that are here locally in this point, you need to have locality there. Locality is important. The more you lose locality, the further off you have to go, the less representative are those neighbors of your locality, right? Your local context. And that is a point. So let's hold that point in mind. And now I'll show you something that is quite remarkable. This is something, I'll ask you guys a puzzle. Think of, don't think Bay Area. Bay Area is a terrible, terrible thing to think. Think of all the neighbors who are not in Bay Area, right? Or not in major cities. Think of your friends who are not in the metropolitan areas. And when you think of them, ask yourself this question. Are they close to either the sea or the Great Lakes or a state boundary? You would be surprised that the majority of them, or a large number of them, would be living in rather along or rather near some state boundary or the sea or the Great Lakes or something. And you can do this experiment, close your eyes, think for a moment. I'll let you guys digest that for a couple of minutes. See if that is true or not. But remember, avoid the metropolis. If you start counting only the friends in New York and New Jersey area and the ones in Los Angeles and San Francisco and Chicago area, you'll be in trouble. Even though one can argue that New York ones are close to water, San Francisco and LA ones are close to the boundary, and so is Chicago. But think of 20 friends or 10 friends, and you'll realize that quite a few of them live along state boundaries or water bodies, large water bodies. Did you get a chance to think through that? All right, I'll assume you did, and or later on you can do that. But I'll give you now a reason of why this sort of things happen, and I'll do that by taking a unit circle. Suppose you have a center, O, and you make a unit circle. Suppose your world is a unit circle. Radius is equal to 1, huh? Unit. Imagine your world as a unit circle. Now, notice this. If I ask you, let us say that your friends are uniformly distributed. Uniform enough, isn't it? Let's take this. They're uniformly distributed. And I ask you this question, how far do you have to go to meet half your friends? Right. So you say, well, that's very easy. Let us say that the distance I have to go is a distance r. Right? So, oh, sorry, something happened. Okay. So you have to go a distance r. You would say that the area, the number of friends inside R area is proportional to pi r squared.
Yeah.
And the total number of friends pi is equal to pi 1 squared is pi, isn't it? So if you want to meet half your friends, the number of friends who are within r distance, that would be equal to pi r squared. What proportion of all your friends are here over pi? Does this make sense? Pi cancels out. So suppose this is equal to a half, right? To meet half your friends, you have to go. So now let's do this. R therefore is equal to 1 over 2 square root. And that is
0.707.
Yeah, 707. Approximately 71%. R is 71%. So let's ponder over what it means. It means that this figure that I drew is not really representative. 70, yeah, maybe it is. Most of your neighbor, do you notice something? Actually, maybe this, maybe we could do a little bit more. This is more like it, isn't it? Is this better, guys?
Yeah.
70%. And so what do you notice? Do you notice a remarkable fact? Half your friends seem to be living along the edge. They are rather close to the boundary. Do you notice that? Half of your friends are very close to the outer perimeter.
Yeah.
They are.
Further.
And that's a very interesting observation. And now observe what happens if I take the unit circle to a unit sphere. Now, from here, let's generalize. Consider a unit sphere. Here, what is the area of friend is proportional now to the volume, and volume goes as 4/3 pi r cube, right? And divided by, if you do it and in the case of unit as a proportion, it would be times 1 cube. And so what will it be? It will be equal to r cube. So if r cube is equal to half, r is equal to the cube root of half, right? Now, try that out, what that comes out to be. If you do that, you will realize that it is close to some 85%. I'm just trying to do it in my mind. A half to the power 1/3. If I do
80%.
80%, isn't it? Is that right?
Yeah.
We could do that in, once again, we can bring up our R and say, if R squared is equal to, R cube is equal to a half, then 0.5 star star, let me be approximate, 1/3. 80%, right? It is close to 80%. So, well, now this disappeared. Excuse me, guys. It seems to run away. Okay, so now you realize approximately 80%, which means that in a three-dimensional space, your other half of the neighbors are within 20% of the distance from the outer edge. Do you see that, guys? Does this make sense?
Sure.
I.e., half here are within 20% of the edge. Now, what happens if you take R is equal to 100? Let's say 100 dimension. If R to the 100 is a half, then R is equal to 1/100. Let us try and see what that comes to. Right? Actually, forget 100. Let's just go to 10 dimensions. Let's see what happens in 10 dimensions. You go there and you say that 0.5 star star 1/10. Guys, can you guess what it will be when I hit enter?
0.001.
0.99.
You'll be surprised. It's 93%. What does it mean? Most of half your neighbors are living, half your friends are living practically within sight of the border.
Within the boundary, yeah.
And if you go further to 100 dimensions, see what happens. It turns out that to meet half your neighbors, you practically have to go over the whole unit sphere or hypersphere, isn't it? If you take a 100-dimensional sphere. Now, do you see what I'm getting at, guys? So what it means is that it means something quite remarkable. Think about it. When you go from a disk, a two-dimensional circle area, to a unit sphere, there is just more volume in the sphere. There's just more space there, isn't it? The intuition is it's more space. You go to 4 dimensions, now the points can move around in even more space. So this, if you try to uniformly distribute the point, they sort of evaporate, they sort of diffuse out away from each other. Are you getting the intuition?
Yeah.
Right? As you go from a disk to 3 dimensions, already the points are sort of lifting up and wandering around, and diffusing around. You go to 4 dimensions, the diffusion is even more. The space, even if you started with a disk of really a lot of points, let's say 100 points, on a unit disk, 100 points may look a lot of points. Neighbors are easy to find. But in a unit sphere, they're not so easy because now there is more space. data is a bit more sparse. By the time you go to 10 dimensions, all those points have just spread out, diffused out. And so your
Hard to
neighbors
find
are
nearest
far
neighbors.
off, isn't it?
Yeah. There are no more nearest. I mean, nearest neighbors are difficult to find.
Yes. And you know what? You say, well, why do I need, if I want to find the nearest neighbors, let us say I want to find just a 10% of the neighbors. Let us see what happens if I do it with just 0.1 and in 100 dimension, I just need 10% of the neighbors, just say very small number of neighbors, a k nearest neighbors I take and do this. And you realize that still it's 97%, isn't it? And you can play this. It's a very surprising game. You can go and say, well, I'll just pick 1 in 100. Let me just take 5 to 10 neighbors, right? And let's say that I have 10,000 data points or something like that. 10 neighbors is not a big, or 5 neighbors. You realize that you can play this game and it is still 95%. You can say, well, I'll take I have a lot of data. I really have a lot of data. I have, 100,000 data points and I'll take k is equal to 10 or something like that. And so you do that and still you're going the whole distance. Do you see this, guys? I can go on making your, one way to simulate a k is by taking a smaller and smaller fraction. Nonetheless, in higher dimensions, you have to go very, very far in the feature space to capture the neighbors that you have. Am I able to convey that intuition to you guys?
Yes.
So the problem, that is called the curse of dimensionality. When you have to go far to find the neighbors, those neighbors are not representative of your local context. They don't represent that point and what's happening here. And so using those far away neighbors, it's an oxymoron. Far away neighbors are not neighbors, isn't it? And so k nearest neighbor algorithm begins to fail them. Right? So that is the curse of dimensionality. Now, guys, today I wanted to finish this topic of, I didn't reach the kernel so far, and that is in spite of the fact that we didn't take a break. What I would like to do is, let me just review, as in the last few minutes, we review. Next session, we'll take it up from here. And we'll finish this, right? And we will see how kernels, applying a kernels, solves this problem. But think about this, work with this, and see if you got the intuition or not. So let me recap everything that we learned today from the top. We learned that it helps to just look at the neighbors if you have a notion of distance. So if you can find neighbors, and they better be real neighbors, they shouldn't be far off neighbors. If you can, then this algorithm works like a charm, right? So think about it this way: ducks, swans, cows. A situation like this that you are seeing is practically tailor-made for KNN. Would you agree, guys?
Tailor-made for what?
Using the k nearest neighbor algorithm.
K nearest.
Right? So
Yes.
this is also short formed as KNN, right? K nearest neighbor. Little k and NN, capital nearest neighbor. People say. So it's tailor-made for that. The only problem you have to solve is, what is the optimal k? What is the best k that I should use? Right? And then you can go with it, find the best k through hyperparameter search, right? And do that through cross-validation and so forth. You'll find it, and then there you go. Right? It works very well. The places where it fails is when the dimensionality is high, or you can't define the notion of distance. Right? There is no obvious notion of distance between 2 points. Then this begins to fail. Right? You can't use this. On the other hand, when you can, you should always try to use KNN. It's a very simple algorithm, very effective. As you can imagine, it's very effective, right? It captures the local context very well. And you go to the lab and you'll see that it works very well. Right? Next time when we are there, we'll give some time to this.
It is explainable also, right? I think.
It's very explainable, right? So it's a very good algorithm. you should always ask yourself, guys, that, so now we'll go back and look at our problem. In the river data set, could I have used this? Yes, we could. Right?
Yeah.
We could have used it. Dimensionality is low. The notion of distance is Euclidean. And it would have worked like a charm there. Could I have used it for the California housing data set? I leave that as an exercise for you, but can you guess?
Yeah, I think so.
It is a 13-dimensional or 11-dimensional space minimum.
It is a little bit bigger, yeah.
It's a little bit bigger space. So now you have to think whether it works or not. And the way to make it work is actually using another trick. If we could reduce the dimensionality of the problem, and of course also impose a notion of distance there, it would work. Now here is what works here. In this case, there's a cheat. You know the latitude and longitude of that point, right? Geographical. So you can actually ignore a lot of the other variables and you can just ask yourself, give me a few data points near this, geographically nearby. And that could be a pretty good proxy. And you can see what accuracy you get. But California dataset is blessed with the notion of latitude, longitude. You know, that is the quintessence or the most obvious intuition of distance you can get from that. So you can sort of ignore a few of the other variables or judiciously pick only a couple of those other variables and work with those. But sometimes you don't get that privilege. So you can't use the notion in that case. So you have to be a little bit careful. Just because dimensionality is high doesn't mean you can ignore it. So when the dimensionality is high, you can just pick a few dimensions and use that and see if you get away with it. The other thing you can do is this big topic of dimensionality reduction. How do you reduce the dimensionality of a problem? We alluded to that in ML100. You remember, guys, that was the last topic we covered in ML100, dimensionality reduction.
Yeah, the PCA.
Principal component,
yeah. And then we talked a little bit about more sophisticated methods. If you remember, I talked about kernel PCA.
Kernel PCA,
that
yes.
refers to this technology that we just learned on Monday. So we'll use that. We will use kernel PCA to reduce the dimensionality. And then the other thing we'll learn, so if you could reduce the dimensionality, the curse of dimensionality goes away. And therefore, if you have a notion of distance, once again, you can apply KNN. So that's what we'll do. And the next thing we will learn is that actually this business of finding K is a bit of a nuisance, right? So there is actually a way to be insensitive to K. It is using the intuition that the nearer a neighbor is to you, the more representative he is of you or she is of you, right? So suppose you're welcome to take the opinion of the guy who lives in, I don't know, Nevada or Arizona, but weigh the opinion of your immediate neighbors higher, much higher than the opinion of people who are far. If you use that intuition, then you can take pretty, you can afford to go a little bit further out, but you know that their weightage, the weightage you're giving to their values is not as much. Are we getting it? So that is where we'll start with next time on Monday. So if you look at this, suppose you're trying to find the value at A prime, right? If you weigh the local neighbors more, but you still take 30 neighbors, you realize that a lot of giraffes will come into the picture somehow, and cows will come in. But because they are further off, you weigh them down. You say, very little weightage to what they are saying, what those data points are saying. And so you still stay with the prediction that it's a swan. So that is called kernel KNN, kernel-based KNN, right? And so as you notice, this whole notion of kernel is getting more and more everywhere, and it is there everywhere, guys. I gave the talk, if you remember, attention is all you need, right? Transformers and so forth. Now there's a very interesting relationship between kernels, transformers, and RNNs. There's an interesting work somebody came out with, and we'll talk about that. If you guys are interested, I could give a talk on that, but we'll stop here today. I'll field questions now. And the other thing we learned is obviously the curse of dimensionality, right? dimensionality, what it is. Think about it, guys, and try to develop your own intuition about the curse of dimensionality.
Asif, you talked about the California dataset, housing dataset.
Mm-hmm.
You gave some examples. I don't believe we have done that as part of the classes that I took.
You didn't, because you didn't attend the ML100 in the spring.
Okay.
If you had,
mm-hmm.
Yeah, you're right. When I was doing ML100 with your batch,
yeah,
I didn't do that.
Okay.
The more recent edition.
Mm-hmm. How do I get access to that?
I'll give you access.
Okay.
I'm giving you access, the notebook that I'm giving you, the California notebook, has the entire analysis. You have it.
So Asif, it was also covered in I think the Saturday dataset class. So I think Sandeep should have access to that.
Yeah, color. Sandeep has access to it, certainly. Yes, he has. He must be having a notebooks on it. Color.
Okay.
And
no, I think it's no longer on GitHub, right? The 100 datasets.
The idea is that everybody has their local copy now. I sent out an email saying that I'll shut down GitHub, gave more than 2 weeks notice, and then shut down.
Oh, okay. I'll ask him.
Must be having that.
Okay.
Otherwise, I can give it to you. I think somebody else asked it. Abhijit, you also asked for that same data, isn't it? You didn't take a
That is true. That is true. And I'm just waiting still. You said that you will send me the zip file, but I'm waiting.
I apologize. So you
No, don't. That's fine. I understand, man. You are really busy. So, but
Even
that's fine.
I would also need it because I attended Kala and we attended the older ML100.
Kala,
yeah.
Sanjay, I'll give you the California data set for sure, but not the boot camp one.
Sure. Understand.
You haven't attended the boot camp. Otherwise, what will happen is you won't learn anything in the boot camp when you come to it because all the solutions will be for you.
I understand. Also, Asif, before we get into too many question answers, would you talk about the next, or end of this week's your plan? I think you're going to cover multiple sessions. So if you can just give quick idea.
What I was planning to do is some of the topics that are residual, I was hoping I would cover on this Saturday. See, guys, we are now end of 4th week. You realize that we can cover only 2 more topics in the next 2 weeks. So I'll give you a choice what they are. I think recommender system is something that you all would want, just to know how Amazon makes recommendations and so forth, right? And so I'll be talking about the price, a classic algorithm. Now it's called classic, that won the Netflix $1 million prize, the famous thing prize. So we'll go with that algorithm, right? Then that leaves one class. I could do regularization, which is an important topic. You must know about regularization. Or I could pick any other topic that you guys wish.
Asif, have you already covered bagging? You mentioned you're going to do the bagging. Did you do an extra class for that?
Boosting, I'll do in one of the extra sessions.
Okay.
Bagging we did, no? Bootstrap and
boosting, yeah. Stacking, I think. You said you were going to talk about.
So yeah, boosting, XG boosting.
Boosting and stacking, yeah.
Boosting.
So Asif, so for the recommender system, means I know they use it for items. So do they also use the similar logic for their employees, or they use something else?
Okay, that's an off the record conversation.
Yeah.
Okay.
Since I have okay.
Are we going to do anomaly detection, Asif, in this one? Or?
See, anomaly detection, I'll keep for it belongs to the boot camp.
Okay, let's do that.
Here, and you have done it.
Yeah.
Boot camp, isn't it?
Not boot camp.
Oh, you didn't come to the boot camp. Okay.
Yeah. So it's going to be part of deep learning. Then I can pick it up there.
You should pick, because we will do we'll do anomaly detection using deep learning. The anomaly detection without deep learning we did in the previous. See, there are two sets of boot camps. One is all of the tabular data, where deep learning helps, but actually the rest of machine learning is much more effective. And then there are the images and audio and textual data where this works very well. Deep learning works very well. It turns out that deep learning in one area works very well for tabular data, which is anomaly detection. DADs. They're called DADs, deep anomaly detectors.
Is there a recording for anomaly detection by you for not a deep learning, the regular?
Yeah, see, a lot of people were quietly making recordings when I was giving the talk. But at that time, I was still creating the infrastructure for recording.
Okay.
So I did not make an official recording, but I'm pretty sure that I knew that 3 students were recording it on their cell phones.
Any books you can recommend?
Oh, there are outliers. Literally, if you look at the word outliers, there's one Charu Agarwal who has written a fairly comprehensive survey of all the outlier detection methods.
I see.
Title is called Outliers, and there are many other things. See, I can't think of very obvious other textbooks. Usually, if you go to scholar.google.com, you will see that a lot of people have written a lot of tutorials and surveys on outlier and anomaly detection techniques.
Sure.
Anomaly detection is one of those techniques, guys, that if you become good at only that, you can make a killing for the rest of your life. You essentially have a meal ticket.
Yeah, the frauds, the network, all kinds of frauds.
Exactly. And it is big business. You get involved because today, fact of life is that all the crooks are winning.
Yeah, it's always a catch-up game. And yeah, you are right. The crooks are
Abhijit,
winning.
you must be in a networking industry. you
I
and
not.
I are thinking same.
Yeah. Actually, with all this working from home, right, the whole pattern changed. So, they are taking advantage, these guys are taking advantage of that for denial of service attacks.
Thanks, Asif. I will look into it, that book, and probably schedule 10-15 minutes of separate session if needed.
Yeah, guys, let me just say one thing, 1 second. I may say one thing, guys. See, I'm preparing you for the boot camp.
Okay.
In a sense, because when the boot camp starts, it will be more intense. I will be giving you guys these 2 lectures a week and a whole day. Then it will become not 1 day lecture, 1 day lab. It will become 2-day lectures and a whole day of lab from morning to evening.
No, that will be awesome. Yeah.
It will be very intense, but you learn a lot. Those people who attended the last boot camp, I hope they all would agree that you learn almost 10 times what you learn in the workshop.
You're talking about the 100 data sets?
Yeah, the 100 data sets bootcamp.
Yeah.
You agree with that, no, Abhijit?
Yeah, in the back room, you had those presentations and all going on. Yeah.
So in the bootcamp, you learn the whole life cycle of a data scientist, how you do an analysis, how you argue your business case, how you present it, right? And you learn all sorts of very powerful techniques. But it is hard work. You have to commit to it.
Are we going to do it remotely, the boot camp, or
do it remotely.
Is that the plan?
The only difference will be that, see, at this moment, when you do your homework, you do it, you don't do it. I don't really cross-check on you. I have given a reward, which is that people who do all the labs and do their project, I'll be their reference for jobs. But there is no thing. But in a boot camp, you would form large teams of 6. I mean, Sandeep will tell you that, right? Large teams. And there is no getting away from it because every few hours you'll have to present your progress to everybody else.
Yes.
We have at least 3 presentations a day. So each team has to present their work at least thrice a day.
Right. No, what I'm saying is, are we going to do in person or is it going to be remote?
No. Okay. Not in person. I have no intention of infecting you all.
Yeah. This thing is picking up again.
Which means we have to wait for this coronavirus thing to blow over and then we have to go do in the boot camp?
No, we'll do it
online.
To start it. Guys, in 2 weeks, your workshop finishes, which means I should start the registration for the boot camp now. Right? You guys are ready for it. I'll do the boot camp, and in parallel, I'll also start I'm about to start by the way, yes, I should start the registration. Prachi, could you please take registrations for the math behind data science? Or have you already taken some? Do you happen to be here, Prachi? I don't know if you're here. Or Dennis and Glennis, do you happen to know if you ever took the registrations for the math behind data science? So guys, here's the thing. At this moment, right, once you finish ML 200, those of you who haven't done ML 100, by now you should get the feeling that you probably want to go back and do ML 100. On the other hand, if you feel that you can pick it up on your own, then you don't have to go do it. Read it from your book and pick it up. The road forward is two journeys. One is through engineering math, which will once and forever make you comfortable with the math behind machine learning. So typically when you read a research paper or a textbook on good textbook on machine learning, you quickly realize that there's a lot of mathematics involved. That math is not hard. You have done it at some part in your life. It is linear algebra, calculus, and probability. 3 things. Unfortunately, those things you have washed away with all the showers you have taken. So we just need to refresh our minds on that. Also, one of the things is the education, if your education system has been defective. And I must say globally, the one subject that is poorly taught is mathematics. Right? Most people, they just regurgitate what they learn from their teachers or from the books or something. Math is actually the most beautiful subject, and it's really worth knowing it in the right way. And if you learn it the right way, it feels very easy and intuitive. Some of you have taken I noticed the people here, some of you have taken my math. Kala, have you taken it?
No, I haven't.
You have? Okay. And
how many weeks it is, Kasif?
It will be the same 6 weeks.
And it's like 2 classes?
2 classes a week.
So will you be able to do the boot camp and the math? So you are going to interpurse them, or what? How are you going to do?
Yeah. So there is I'll tell you a joke. It's not a joke. In big data, in distributed systems, there is a CAP theorem, right? Which says that between consistency, availability, and partitioning tolerance, you can create a system that will survive if the network partitions, or actually it's not partitions, a modern interpretation is latency, if the latency is too high. Then if the latency is too high in a system, you'll either have to choose between consistency or availability, right? You can't have all of them. If you want to have all of them, then you don't have partition tolerance. You better have a single database like Oracle database, one machine.
Asif, so what is Spanner?
Spanner is a very interesting thing. It's great that you bring up. They do very fast propagation of updates intelligently, consistently. So that's worth of a talk itself. It's a beautiful paper and an amazing implementation in Google. But see, and it really, Spanner is the closest thing to violating CAP, essentially. But yes, you can pick only 2. So in the same way, I would say that when you're doing this subject, right, machine learning, and you're learning, when you do the boot camp and you do a workshop, a boot camp and a workshop together, Abhijit, you'll have to pick up between machine learning, your job, social life, and sleep. You can pick only 3, not 4.
No, that's fine. But yeah, will the classes be interpersed? That's the thing, the math and the boot camp.
Yeah, of course it will be
interpersed.
Yeah,
and naturally, because you are the only lecturer, so.
Yes, I'll be the only lecturer. It will be intense. Right? Or the other thing we could do is I can slow roll the math. I can make it once a week so that it goes on for the usual 3 months.
Because I like to do the math once, actually. At least I would like to refresh.
The one that usually goes houseful. People love it. So, Ajay, do you remember the math class? Did you like it? Anybody here who took my math class?
Yeah, I think that's the best class.
No, it was. I think it's one of the best.
Yeah, it's the best class. I must say.
Okay, so but I need to get a little bit more organized. I need to create a registration and some notifications and all that. I'll do that.
So Asif, are you not thinking deep learning bootcamp or?
No, bootcamp, deep learning bootcamp is about to start in 2-3 weeks. Get ready for it, guys.
But you are saying deep learning and machine learning and math, three.
No machine learning. At this moment, I'm not
Okay.
offering the other bootcamp.
Other boot. No, you're not bootcamp. Okay.
I'm only offering the deep learning bootcamp.
Okay.
But the deep learning will be a series of bootcamps.
Yeah.
It will be intense.
Thanks.
Deep learning has become a vast field, right? So I cannot teach it in a standard workshop setting and do justice to it. You won't learn enough. The only way to do that is to give 2 theory sessions a week and a whole day to labs.
Got it.
So we'll do a lot of it together.
Prachi just messaged me. She has been taking names for the engineering math.
Oh, she has been taking. Okay. So guys, if you want to enroll for all of this, we can agree on the dates, convenient dates. But the bootcamp, deep learning bootcamp is starting. I'm just waiting for you guys. I wanted it to be a natural transition for you guys. If you are taking the deep learning bootcamp, please register right away. That is one class that may fill up too quickly. Well, these days we live in the COVID world. Who knows? Maybe it won't fill up. But that usually is very highly anticipated. Right? Send your names to Prachi quickly. And when I send you the registration form, do fill it up because it will be first come. In case it is it becomes too popular, it will be first come, first serve.
What is that? It is called Teach Me a Math or Engineering Math. What is it called?
Yeah, it is the Math 100 course. We call it the Math of Data Science.
Math of Data Science.
A Math Behind Data Science is the actual name, Math Behind Data Science. More colloquially, we just call it the engineering math class because pretty much what you did in your college. Did you guys ever take engineering math in college? Anybody?
Yeah, Krasik.
Yeah, Erwin Krasik. Yes, exactly. Yeah. But this time I'm changing the textbook.
Oh, you're changing it to what? No.
I'm changing it to a book which is a little smaller, but it is much more focused on just the math behind data science.
Oh, okay. Yeah, that will be better. Yeah, the engineering math was a lot of math, but then it actually was talking about other things like physical models and those kinds of things.
That's right. The engineering method. Erwin Krasik is a classic. Yeah. Like all of us who went through IITs, and I think all engineering colleges use that. In US, they used to use that. In India, they used to use that. Yeah. I don't think the author is alive anymore because you don't see any new editions.
Yeah. I think 10 was the last one, I believe.
Yeah. We learn from a new book. All right, guys. And somebody had a question that I interrupted. Sonal, how are you liking it so far? Are you getting anything out of it? You're very quiet.
Oh, it's a little bit hard for me.
Yeah, I'm sorry, I didn't hear that.
It's a bit hard.
It's a bit hard. Eh? Reach out to me if you need help, Sonal.
Okay.
Remind me, which grade are you in?
I'm going to 11th.
Oh, yes, it would be hard for you. You're getting a very early start onto all of this. Kamya, how about you? Let me ask all the young ones. Kamya, are you hearing me? You're on mute. I think she has stepped out.
She is on mute.
Aditya, you also have come into the subject, right? You have a PhD in a quantitative field, but machine learning is new to you, isn't it?
Yes, yes.
Are you finding it manageable or are you finding it a bit hard?
I understand the theoretical aspects of it, but implementing it on the code, that I think I have some challenge.
Aditya, libraries and code you become familiar with. You notice that now that I go through the solution of support vectors and random forest, it all begins to look very familiar, isn't it?
Yes, yes. That is true.
Coding is the easy part in machine learning. It's not the hard part. That will easily come. Let me ask.
Actually, mostly we are facing problem with these versions.
With
library versions.
Oh yeah. See, here's the thing, guys. Software engineering, there are like every field has some nuisance.
Yeah.
The software engineering is always the library versions.
Yeah.
In the world of Windows, it used to be called the DLL hell.
Yeah.
The jar hell.
Yeah.
So library versions is always a big pain. And installing the library, and one library won't work on this machine.
Yeah, exactly. That's what we are facing with that pandas. I made it work, but it is not giving exactly the same output what I got from you. So I think still there is it is working, but it's probably not the latest, I believe.
You sit with me, Vijay, take some time.
I think that is the one, what's her name? Bhuwana was talking, because she's in the same team. I think that's the help. Yeah, we will sit with you maybe tomorrow, and then
Bhuwana, how about you? Are you able to follow through all this?
Yes, Asif, like it's better now. I think I need to practice more, and the theoretical part, like I'm pretty much good, and I went back to ML100 and I was checking out few things in R. So now it's a bit better, but I still have some questions to ask you. Yeah, and I'll talk to you about those things.
Definitely, guys. Remember, you can reach out. Prachi is there. She has been helping a lot of people. Dennis is here, and Glennis too is here. You can reach out to any of them, and they'll be very happy to help you. These are the TAs for the class. Keep reaching out to them. If you see I'm busy, reach out to them. Then, if you feel you still need me, definitely reach out to me. That's that. Who else should we ask? Harini, how about you? You also have come. You haven't taken ML100. How are you finding it?
As if same here, the theory I'm able to understand with a bit of reading and all that. But implementing it practically, I'm having issues. Like I have sent you my R code. I think that looks really, I don't know what you would make out of it, but yeah, I'm stuck at places. So even though I'm going back and reading to find the code, I'm not able to implement it and, into what we are doing.
Okay, we'll sit together and say,
It takes a lot of time.
With Prachi or Dennis or Glennis?
I haven't. I will speak to them.
They can help.
Okay. Yeah. I'm still stuck in the river data set, so that puts me a lot behind. And
the first analysis is the hardest, Harini.
Yeah.
Going to the first. After that, it becomes sort of repetitive.
Okay. So I'm stuck at the model building stage again. So anyway, I've sent you my code, but whenever you have time, or I'll reach out to Prachi and see if she can.
Yes. I'll try to reach out to you, but in the meanwhile, don't wait on me. I stay very busy.
Okay.
The TAs.
Yeah. Otherwise, yeah, a lot of things I'm understanding very well. So that's good.
Excellent.
Asif, I'll take this opportunity. I think Sandeep had a question about his project. I don't know if you can take the time to see. He did something and he sent a question to you. He's not here right now at the moment. Yeah.
Oh, he's there, huh?
No, he's not here. But I just, people are asking for help. You just said you will.
Yes, certainly. I'll look at his, I'll check my email. Actually, I've been extremely busy. I haven't checked my.
I recognize that. Yeah, I realized that. So I just I thought I'll remind you. He just sent something. Some bipartite something. He was telling me about it, and
oh, he already made the bipartite drive. Okay, that is good. Yeah. I know what he's talking about.
Yeah, so he did something because he talked to you and you gave him some idea. He worked on it, and then he got something, and looks like he's stuck or something. I don't know. I'm not sure. I did talk. He's working on something. He's not here right now.
Tomorrow noon, I can reach out to him.
Yeah, please. If you could take some time and just give like 10 minutes maybe, and so we can make some progress. Yeah.
I'll definitely do that. All right, guys, if you don't have any other questions, I'll close this meeting. I wish you all good. See you then on Saturday and Sunday.
Thank you. Thank you, sir.
Thank you.
We are having this week we are having a seminar. It is the seminar that the Support Vectors is hosting is by very illustrious person, a person who is often the advisor to the Prime Minister of India. He was a person who graduated from IIT, like us, one of the top rank holders, then gave up his engineering thing. He said it's all useless. It doesn't benefit mankind at all. All that people do is work for companies. He went off to the hinterland, to the villages, to see how real people are living their lives and what their real problems are. In his words, spent a lot of time studying their life, and then he has given his life to creating engineering solutions which are specifically meant for them, that big companies wouldn't care about or so forth. And he has been a serial entrepreneur, created a lot of things, and he has made a lot of difference to things. He is now an honorary professor at IIT as well as entrepreneur. And almost every Prime Minister of India in the last few sequences have reached out to him for advice. So he'll be the speaker on this Saturday's talk. He will talk about AI and what it means, again, to the topic in hand, to people. How can you bring it to help people?
Oh, that'll be awesome.
Yeah.
What's his name?
Kannan. Well, I don't know what his full name is. See, he's my friend's brother. Okay. And I only know him as Kannan, which may be his nickname, so I shouldn't embarrass him in public. So
What time, Asif?
Sunday noon.
Okay. Oh, nice.
Thank you.
Are we going to do the starter code for the project on Saturday?
Yes, we'll take time. We'll do that. Actually, guys, I have to just, unfortunately, I'm really crowded on time. One way or the other, I'll find time, and I do want to get you guys started on the project. Maybe if needed, we may not have a Python session this week. Python, we are essentially done, guys, or do you guys need more sessions? Anybody has a feedback? Do you guys?
Python, you have told us what our libraries will be using, Asif, and pandas was a little bit you went in detail.
Right.
Okay, so I don't know whether you want to continue that, but you said you would parallelly do R the other day.
Yeah, I wanted to start on R now. So maybe I'll give a week's gap, use this week for the projects, and after that, get into R.
Okay, thank you.
Giving background on R. That's sort of overdue.
So Asif, you have sessions on both the days, Saturday and Sunday?
Yes, I do have sessions on both the days. Saturday, I have there are two things. Saturday noon is a quiz, guys. You guys know, right, that there's a quiz every Saturday noon.
Yes.
Yes.
So
are you recording, Asif, those sessions?
Yeah, recording. In fact, Prachi has that. She will be
okay.
To the YouTube.
Okay.
So this week topic for quiz, Asif?
Random forests.
Random forest. Okay.
Last time it was decision tree. It is random forest. I might also include support vector machines. Right. So two topics. It may be a longer quiz. Come to it, guys. It's interview preparation. You know, it just validates whether your foundations are as good as you think they are. Decision tree, I was very pleasantly surprised. Most of you got most of the questions right. So that's good. It means you are reviewing from the book also. And I hope we get similar results for random forest and SVMs. Let's stop with that, guys. Go have a pleasant evening. And I can smell it, so I better run. Thank you.
All right. Thank you. Good night.
Sure.
Good night.
Night, Asif.